This is Lab 5, A Ball on Mars Simulation by Sayce Parekh. The objective of this lab is to use fundamental physics principles to analyze how gravity and air resistance affect motion of a projectile on different planetary surfaces, and compare the effects of drag and gravitational acceleration on horizontal and vertical motion using computational modeling. These were the fundamental physics principles that we are using in this lab. Newton's second law, which is the net interaction between system and surroundings, which is the net force, to the observed motion, which is the change in momentum. From this law, we can get the position update formula, the velocity update formula, and the momentum update formula. We also have a gravitational force, which is the force that attracts and that pulls objects that have masses together. Then we have drag force, which is the resisting force that resists the motion of an object moving through a fluid. If there's no drag, then F drag is equal to Fg. And in the simulation, we use the momentum principle to update the velocity and position. Then we also have a coefficient of restitution, which was used to simulate the bouncing after the ball hits the ground, but this behavior was not the focus of the experiment. This is a preview. The balls on Earth fall faster because they have stronger gravity compared to the balls on Mars. And then drag causes the ball to slow down, but with Earth's drag having greater effect than Mars because Earth's atmosphere is thicker. And overall, the gravity affects the vertical motion and drag reduces the horizontal distance. The system is the balls, and the surroundings is everything else. My procedure, I created a computation model to simulate the motion of an object in projectile motion under the influence of both gravity and air drag in different planets, and then I ran a simulation to generate a position time data for both x and y directions, and then the velocity and time data for x and y. A reference, the gravitational acceleration for Mars is 3.73 compared to 9.83 on Earth. The drag coefficients for Mars is 0.0016 compared to the 0.01 for Earth. They estimate because Mars has 1% of the atmosphere of Earth, and these are my citation. My code, and these are initial conditions. The mass was 0.045 in kg. The initial position was 0.96 in the y direction. The initial velocity was 3.5 in the x direction. This is for all balls. And then I had to offset the balls with no drag because they were overlapping, so this is the code for that. And the constants were the gravity for Mars, which is 3.7, gravity for Earth is 9.8, the Mars drag coefficient, the Earth drag coefficient right here, and then this is the code for the balls, which is the F grav equation right here, and then the F drag equation right here, and then F net, which is F grav plus F drag, then Newton's second law, which is the velocity update formula right here, the position update formula. And so the balls plus drag is red. The Mars plus drag is red. The Mars with no drag is orange. The Earth plus drag is blue. And the Earth with no drag is cyan. This is a video I got from the code. These are the graphs that I got from the code. Let's look at the x versus time graphs. As you can see, the cyan and orange, which are the balls that are not affected by drag, are basically identical. So I had to offset them so they didn't overlap. But we can see that gravity has very little effect on the x versus time graphs. We can also see that Earth travels shorter distances and is slower than the one on Mars, and this is due to Earth having a thicker atmosphere than Mars. Now let's look at the y position versus time graph. We can see that the balls on Mars travel greater heights than the balls on Earth. This is due to Mars having less gravitational acceleration than Earth. We can also see that the balls with no drag travel farther than the balls with drag in the y position. This means that drag has a effect on the y position. Then in the y velocity versus time, we can see that Earth's velocity is greater than Mars' velocity because the gravity is stronger in Earth, so it'll move faster up and down. And since there is no air resistance, the balls without drag travel are faster than the balls with drag. These are my sources of error. It's a simplified drag model, but real air resistance depends on the object shape, air density, and flow conditions, which are not fully represented in this lab. There's no rotation or spin. There's constant gravity, but it varies. There's uniform atmosphere, but it varies because air density changes with height. And then there's no friction. If the ball had twice the mass, how would it affect the motion on Earth and Mars? Without drag, the motion would stay the same. Gravity affects all masses equally, but with drag, the heavier ball will lose less speed because it has more inertia. As a result, it would travel farther and be less affected by air resistance on both planets. What does it mean that the ball traveled further on Mars than on Earth, even though it had the same initial speed in both cases? And then what does it tell us about the influence of gravitational acceleration and drag in the projectile motion? So it shows that weaker gravity and less drag on Mars allows the balls to stay in the air longer and travel further. Both gravity and air resistance significantly affect how far the projectile goes, even with the same launch speed.